Good afternoon, everyone. My name is Alkesh Srivastava. I'm a researcher at the Motion and Teaming Lab of University of Maryland College Park, and today I'll be talking about my research on path-based sensors. I will be focusing specifically on the question, will the knowledge of correlation in random variables accelerate information gathering? Now, before I start my presentation and try to address this question, I want to bring your attention to the keyword path-based sensors. Many of you might be familiar with what path-based sensors are, and many of you might not be. So therefore, it's my duty to first establish the definition of path-based sensors so that we can have a healthy exchange of information here. So what are path-based sensors? Path-based sensors are theoretical sensors. They are a conceptual idea. These are not those sensors that you embed on a robot to sense different things in an environment. To better understand what exactly path-based sensors are, consider this example. Consider an environment, a communication denied environment, where there are trapping pits that are spread everywhere. Now, these trapping pits may trap your robot, may disable your robot, or even destroy your robot, and therefore you want to avoid these locations because this will result in loss of wealth of information, and at the same time it will also result in loss of the robot itself. Now, because this environment is communication denied, you don't exactly know where these trapping pits are, because inside a communication denied environment we don't know what is happening if we are outside this box. So one of your target is to locate these trapping pits so that you can avoid going to those locations and avoid loss of robot and loss of information. Now assume that you ask your robot to follow this particular path, and the robot always follow the trajectory that it has been assigned to. So that is, it does not deviate from the assigned trajectory. Now, as soon as this robot enters this environment, this communication denied environment, it will be invisible to you. And as you can see right now, it got trapped by a trapping pit. But outside this environment, we don't know what was happening. We don't know whether the robot was trapped here, whether the robot was trapped here, or it was trapped exactly at this location of the trapping pit. All we know is that the robot did not come back. So outside this box, we know only two pieces of information. We know the path the robot took, and we know that the robot did not come back. Such an observation are known as path-based sensor observation. So an observation where you know that an event has happened somewhere along the path, that is the trapping of the robot may have occurred anywhere on this question mark. So if an event has occurred somewhere along the path and we don't know where exactly that event has happened, then such an observation is known as path-based sensor observation. Now that we have established what path-based sensors are, let me move to the initial question that I was trying to address, whether the knowledge of correlation will be helpful or not. This will be the basic outline of this presentation, and I will start by motivating why this question is important. Knowledge of correlation is relevant in many applications. For example, in search and rescue mission. In search and rescue mission, our targets are human survivor, and in most cases, these targets are trapped near hazardous location. So there exists a correlation between hazardous location and the location of our target. Similar correlation is obtained in mining operation where useful minerals are obtained near harmful locations. So there exists a correlation there as well, and it is very relevant while detecting the source of nuclear radiation. In nuclear disaster where there is a nuclear radiation leakage, we want to know where exactly the source is. But when we send a robot, due to radiation exposure, the robot may get disabled. So here as well exists a correlation between hazard, that is nuclear radiation, and the source of radiation, which is our target. So this question is really important and relevant to the robotics community. So let's talk about the problem. Let's talk formally about the problem that I'm trying to address. Assume that you have an environment, a communication denied environment where communication is forbidden at all time, and we have in total M agent. The environment will be discretized to allow the modeling of a probabilistic graphical model. This will help us in doing the Bayesian network analysis that we'll be discussing in a few slides. And in the discretized environment, a given cell may contain the hazard or may contain the target, or it may contain both hazard and target, or it may contain neither hazard nor target, so it can be totally empty. And in such an environment, our objective is to efficiently and robustly gather information about target X and hazards Z. Throughout this presentation, we'll be using Z for hazards and X for targets. To address this problem, we'll be using a Bayesian network approach. Let's take the example that we just discussed to define what path-based sensors are. Now, let's assume that the robot took this particular path. As mentioned, we'll be discretizing this path, so let's do that. After discretization of this path, we can do a cell-by-cell analysis, and in each of these cells, there may be a hazard or there may be a target. So we'll assign the random variable Z and X for the analysis. So let's take apart these cells and try to make a Bayesian network out of this right now during this presentation. So let's make an assumption that the robot traversed through this path, each cell C1, C2, C3 through CL. Now, we know that in each of these cells, there may be a hazard or there may be a target, as was discussed earlier. Now, to model this Bayesian network, we'll first assume that in each of these cells, there can be a hazard Z. Now, each of these hazards in their respective cell may cause the destruction or the trapping of the robot. That is denoted by delta. So each of these hazards may cause the trapping of the robot, which is shown over here by delta. And there is a causal link between hazard Z and trapping or destruction of the robot, delta. Now each of these cells are independent of each other. Therefore, if the robot was trapped in any of these cells, or if the delta 1 is happening in any of these cells, that may result in a path-based sensor observation. So hazards cause the destruction of the robot, and destruction of the robot in any of these cells will yield a path-based sensor observation. So this domain knowledge results in this particular Bayesian network model. It's not over yet. We have mentioned that there exists a correlation between hazards and target. We can model this correlation by just simply adding an arrow between a hazard and a target, and we establish that there exists some correlation between hazards Z and targets X. So why we plan to use a Bayesian network? If we use a Bayesian network, we get this joint probability distribution, which you can see on the screen. Now, Bayesian network provides us the flexibility to update target belief based on path-based sensor observation. This was not done in many of the previous work in similar domain. Whenever we had the destruction of a robot, we were not updating anything about the target. But because there exists a correlation and we can model this knowledge of correlation using a Bayesian network, we can update target belief map based on a path-based sensor observation, which is really, really useful in this particular case. Based on this Bayesian network and this probability joint distribution, we formulated an algorithm called kappa BNITP. The details of this algorithm is present in the paper. Feel free to read it and reach out to me if you have any question about it. But I'll directly jump into the results due to time constraints. So we conducted various experiments and we found some useful results, some good, some bad, and I wanted to share them with you on this workshop. So kappa BNITP, the algorithm that we introduced, gathers more information when adversary lethality is moderate, 50% or 60%. So what do we mean by adversary lethality? So assume that you have a cell. If your robot enters that cell, if there is a 50% chance that the robot will be trapped or destroyed and 50% chance that the robot will survive it, then the lethality of that cell is 50%. So that's the definition of adversary lethality. So we found out that when kappa BNITP is executed in a moderate lethality environment, then it outperformed the previous state-of-the-art algorithms, which are relaxed ITP and relaxed BNITP. But when the adversary lethality is either very high, like 90%, or low, like 10%, then kappa correlation produces noisy updates, leading to noisy information entropy decrement and some false results in the estimation of the environment. So kappa BNITP is useful sometime and it is not useful in other environments. So what are the key takeaway of this talk? Bayesian networks are useful for incorporating correlation in random variables. as we can see that we used this Bayesian network knowledge and we were able to formulate incorporate the correlation in random variables. Incorporating correlation accelerate information gathering, as it was shown in the previous slide, that when the adversary lethality is like 60%, then the information gathering is it's really nice, and it's better than the previous algorithm. So that's a good thing that correlation does work. However, further investigation is necessary to generalize well over various lethalities. So that was all. Thank you so much for your attention, and if you want to know more about path-based sensors, you can scan this QR code or follow these references.